Okay, so let's take a look at our final idea of the kinetics unit, and that is reaction mechanisms. Reactions can occur all at once or through several discrete steps. Each of these steps is known as an elementary reaction or an elementary process. So here you have some examples of different kinds of reactions. You can have one molecule starting off, so this would be like a decomposition reaction, known as a unimolecular molecularity. Say that word fast. Molecularity. So molecularity is just telling you how many reactants you have to work with. So in this case, we've got one reactant, so the rate is obviously dependent upon how much of that you have. You can have a bimolecular molecularity, where you have two of the same reactants or two different reactants. But either way, the overall rate law is dependent on two molecules, or the rate of that step is dependent on two molecules. Here's tertiary molecularities. Again, doesn't matter how many of things you have, as long as you have three of them, you're going to see the expression based on what's involved. Three of them, it's a squared. Three different ones, you're multiplying them by each other. Okay, so the molecularity of the process tells you how many molecules are involved in that particular step or process. It could be overall, or it could be individual steps. The important thing to remember, however, is the rate law for an elementary step is written directly from that step. So notice here you've got A, B, and C in the rate expression, A, B, and C. So these represent an individual step. And the rate law for that individual step is a direct reflection of what molecules are involved in that step. This is not the overall rate law for the reaction. This is the rate law for the individual step of each of the mechanism. Okay, so what if we have multi-step mechanisms? Oh my gosh, why is it doing this? So in a multi-step process, one of the steps will be slower than all the others. So overall, the reaction cannot go any faster than the slowest step. It's the rate determining step. So think about cars on a road. If you have a lot of cars coming into this first plaza, them getting through this first plaza is what's controlling how fast the cars can go further on down. But if the backlog occurs at Plaza B, doesn't matter how many cars are coming into Plaza A, here's where the backlog occurs, so the cars wind up slowing down at Plaza B. So the rate determining step is always the slowest step. So the cars can't go any faster than it takes them to get through the slowest plaza. So here's another example of a real chemical reaction, and taking a look at the different speeds of steps. So what if the slow step is the very first step? So we're going to take a look at this reaction. NO2 plus CO gives you NO plus CO2. We know that the rate law for this reaction is actually NO2 squared. It's second order for NO2 and no order for CO. Zero order for CO, but second order for NO2. Well, you look at the overall reaction, you have no idea how they come up with that, right? The mechanism will let us predict how it must happen in order for us to come up with a rate law that looks like this. So CO is necessary for the reaction to occur, but the rate of the reaction is independent of it. So we know that for sure. So the CO is not part of the slowest step. NO, however, is part of the slowest step because it appears in the overall rate of the reaction. So this suggests that the reaction is going to occur in two steps. So here's a proposed mechanism. If in step 1 we have NO2 combined with NO2, you get NO3 and NO. So here we're taking two of these. That's where we get the second order from. We're taking two of these, combining them, or technically moving one of the oxygens from one to the other. So you wind up with an NO3 and an NO. So NO3 is technically an intermediate because notice that it comes into play in the next step. So it appears, but then it disappears. In the second step then, this NO3 is going to give that oxygen that it got to CO in order to make CO2. So in the first step, we create one of the products. In the second step, we create the other product. But the first step happens more slowly. So the rate of this reaction is dependent only on how fast these two things can react with each other. It's irrelevant how fast this reaction happens because apparently this step happens faster than this step does. So the rate is only dependent on the slowest step. And like I said, NO3 is an intermediate. It's produced in the first step and then consumed in the second step. It is the way that NO2 is going to transfer its oxygen to CO. Because CO is not involved in the slow step, it does not appear in the rate law. So basically what you're seeing is the first plaza is where things are slowing down. So maybe there's only one lane open and that's why all the cars have to slow down. Who knows? You guys figure it out. But there's the analogy, okay? So here's an example. The slow step controls the rate. In this case, the slow step is the first step. Once you're through that slow step, you can go as fast as you want through the rest of them. Okay? But what if the initial step is fast? That changes things a little bit. Okay, so here's an example. I've got 2NO plus Br2 yields 2NOBRs. The rate law for this reaction is actually NO2 squared times Br2. All right, so right away, this would require like a 3-particle collision for it to work completely. That's what this is saying. 2 of this and 1 of this, you're not going to have that happen in one step. So there's some sort of mechanism. So what can we figure out for the rate to be dependent upon both NOs and Br2s? And like I said, there's no way that it's going to be a tertiary or a trimolecular process. So we've got to have a bigger mechanism. So since we know that everything's involved, here's a proposed mechanism. The first step is going to be fast. The second step is going to be the slow step. So the second step is really the rate determining step. How do we know this? We've been able to measure it experimentally in the lab. Okay, so this is the proposed mechanism. You take NO and Br2, create an intermediate, NOBr2. Then what happens? NOBr2 is going to react with the second NO to create the 2 NOBRs. Okay, how that happens, what collisions have to take place, we're not worried about that at this point. So don't worry about how things have to actually collide in order to get it to work. Okay, so step 1, notice, is at equilibrium. It includes both the forward and the reverse reaction. That means that this thing could go on to collide with an NO and make the product, or it could go back and do NO and Br2 and just remake the reactants. Okay, so since the overall rate depends upon the slow step, we know that the rate law for this step is going to be NOBr times NO, and then the rate constant for step 2 is K sub 2. Okay, so that explains the rate law for this. But how do we measure this guy? It's an intermediate. It's not, you don't have starting concentrations. You don't have anything to measure its presence. So we have to do it a little bit differently. Since NOBr2 can react in two ways, it can react with the NO or it can go backwards. It can decompose to give us our reactants. The reactants and the products of the first step are in equilibrium with each other. Okay, so we can say the rate of the forward reaction is equal to the rate of the reverse reaction. So what does that mean? Because these two rates are equal, I can write the rate loss for them. So the rate of the forward reaction, my reactants, is going to be K1 times the concentration of NO times the concentration of Br2. The reverse one is going to be K -1, because we're doing the reverse, times the concentration of Br2. Okay, now remember, in our rate determining step, in the slow step, we needed this concentration. Well, if you look at this equation, we now have a way to represent this concentration. If we take this reaction and rearrange it, you can see that the concentration of NOBr2 is equal to K1 divided by K to the -1 times those concentrations of NO and Br2. So we are going to take this whole thing and substitute it into our slow rate loss step for the NOBr2. So if we do that, we get all the K's, second K, forward K for the first, reverse K for the first, and then these two concentrations represent the NOBr2 concentration. So look what we've just done. We have NO times NO, or we have NO squared, times Br2. That's our rate law for the reaction. So that's how you wind up with that. So let me go back. We can talk about this in class more, but that's how you have to deal with a situation when it's not the first step that's the slow step. The first step is going to be used kind of like we did it here. You're going to see a pattern, just like we did with this one. Okay? All right, so I'm going to pause here and we'll get to the next example in the next video.